Our project explores potential strategies to improve the accuracy of current TCN baseline models for estimating hip joint moment for assisted robotic exoskeletons. Exoskeletons are a very important technology that can help disabled individuals, can provide rehabilitation for lower limbs, and also reduce the energetic cost of daily activities like hiking. To kind of provide some domain knowledge for this project, we'll focus on hip exoskeletons, which provide torque assistance directly to the hip joint to reduce the energetic cost of walking and improve walking stability. And it's important that this torque assistance is timed correctly and given in the correct magnitude. It's also important for hip exoskeletons to be able to adapt to many new users and apply across many different walking conditions. To provide some background on how deep learning is integrated into exoskeletons, usually there's large data sets with many subjects and many different types of walking conditions that are used to train temporal convolutional networks. And then these networks are then loaded into the AI computer onto the exoskeleton, and in real time, sensor data from IMUs are fed into the model, and these features are extracted. And using the pre-trained model, the models basically predict the torque at the joints and then provide the appropriate assistance via the motors in the exoskeleton. For the purposes of this project, we'll be attempting to improve the accuracy of state-of-the-art models by applying novel transformer and attention mechanisms, which have never been done before in the field. And we believe these will really capture some of the cyclical nature of gait patterns and improve accuracy by reducing the impact of sensor noise. We'll also implement an ensemble approach to try to create more generalizability across subjects. For this data set, we had 25 able-bodied subjects, and we were provided lower limb joint angles as well as sensor data.
The baseline model consists of 5 residual blocks, each comprising 2 one-dimensional causal convolutional layers. Each layer is followed by a weight normalization layer and a ReLU activation function. The dilation factor increases exponentially every second layer. Each residual block is comprised of 2 one-dimensional convolutional layers, each followed by a weight normalization layer and a ReLU activation function. The authors tested their TCM model against 2 other common models and had about 10% increase in the accuracy. They also executed a hyperparameter sweep for this model and selected these parameters. Here is a visual representation of the results of their model versus the ground joint torque, which is determined by motion capture. Gaps between the lines indicate the errors for the estimation.
TCN is the current gold standard for hip joint torque estimation. Therefore, we decided to build upon the baseline model by using improved hyperparameters, such as the type of optimizer, the number of layers, and the amount of weight decay, etc. We also noted that the original paper did not normalize input features or perform data augmentation, so we also experimented with these approaches. Overall, we did not see consistent outperformance compared with the baseline model. What did work for us was using an example. Here's a look at the data augmentation approaches that we tried. We selected add noise and quantize and convolve to use in our TCN variant model.
So this is the ensemble method we have implement. So here the model trained independently and also the prediction are independent. And then we make an we update weight based on the loss. So the intuition of this formula is the lower loss get the bigger weight. Finally, we got an impressive 19% decrease on the validation loss. The limitation of our model is the overfitting problem and still the low accuracy. So in the future, we think like we should adopt more advanced ensemble techniques. Also, we should amount the number of models and the amount of data. Thank you so much.